We're moving on to a new chapter, chapter 19. This one is about electric potential and capacitors. For our next few mini lectures, we'll be talking in all kinds of different ways about electric potential, which will prepare us to talk about capacitors and then eventually take us on to talk about circuits and batteries. Now, this is a really pretty, I think, image of electric potential surrounding two opposite charges. Actually, we've got our two opposite charges here, and we have our electric field lines that are being mapped in this image, and those are our black lines here. The colors that you see here transitioning from yellow to more purples and blues represent the electric potential that surrounds these charges. To talk about electric potential, we need to talk about work. Remember work from last semester? Well, it's coming back here. When we talked about work last semester, conservation of energy was a very powerful tool for understanding the motion of mechanical systems. We can also use conservation of energy and work to understand the motion of charges. Now, from our study last semester of conservation of energy and gravitational potential energy, as we move a book from some lower position to some higher position, we are doing work on the book. We are doing work against gravitational potential energy. Our gravitational potential energy was mgh. M is the mass, g is our 9.8 meters per second squared, the surface gravity of our planet, and h was your height above the ground. So when we lift a book upward from low potential energy near the ground to high potential energy above the ground, we are doing work against gravity. We are changing our potential energy, but we're also doing work. And this work that we did, since it was against gravity, is minus the change in the gravitational potential energy. The change in potential energy is always your final potential energy where you end at some point B minus your initial potential energy where you begin at some point A. Then you might imagine that the work we do to move a charged particle also has some change in potential energy. Imagine that we have a whole bunch of source charges here. These are positive charges in this case, a whole collection of positive charges. And we have a little positive charge that's over here. Our hand, if we want to move this charge closer to this collection of source charges, our hand must push on this charge in order to move it closer to this collection of source charges here. Since these are like charges, they're going to want to repel. So we have to do work to move our charge from here to here. We have to transfer energy into the system in order to move this charge, because this charge wants to be away from these source charges, not close to it. The work that we do in this situation is minus our change in electric potential energy. Our potential energy when we're at point B here, minus our potential energy when we're at point A here. The potential energy associated with our kind of charge system is what we call the electric potential energy. We can determine the electric potential energy of a charge when it's at any position by computing how much work it took to move the charge to that position. So our work is our change negative. Our work is minus the change in the electric potential energy. So we can figure out how much work it took to move that charge to that point if we know the difference in potential energies between the 2 points, its starting point and its ending point. Now, I know there's going to be a lot of terminology that's a little bit hard to keep separate in your brain. We've already talked about electric fields and electric forces and how those are different. Now we've got electric potential energy and electric potential. So the electric potential energy is different than the electric potential. We define the electric potential as capital V in this case. Or sometimes instead of just calling it the electric potential, I'll just call it the potential. This electric potential or potential is equal to the electric potential energy per unit charge. So we've got another thing that's a per unit because our electric field was the electric force per unit charge. Our electric potential is the electric potential energy per unit charge. Now, we can also define something that we call the change in potential, which we represent by capital delta V here, okay? Sometimes this is also called the voltage. And when we're talking about the voltage of a battery, it's this that we're talking about here. It's the change in potential between the positive and negative terminals of a battery. For example, that's just one example. But you can have a change in potential across a bunch of different systems, not just a battery. Our change in potential is equal to the potential at point B, which is our final point, minus the potential at A, which was our initial point. And so we can also write this as delta V, that's equal to the change in potential energy over the charge. So you can also rewrite the change in potential energy as Q times the change in potential. This equation is going to be useful for us in many different ways. It's on your equation sheet. It's written as the change in potential is equal to the change in potential energy over the charge. On your equation sheet, this quantity is labeled as voltage, but it's the same as the change in potential. Our units on potential, our units on the change in potential, are units that we call volts. 1 volt, another capital V, is equal to 1 joule per coulomb. So that's how the volt is defined. There are many systems where you can define a potential difference within them. You can take 2 points within the thing and define 1 point to have some quantity of potential, the other point to have another quantity of potential, and then you take the potential difference between those points, and that's what we're looking at here. So we've got brain activity that can be measured at our scalp, by putting like little probes or sensors on them. And with that, we can quantify a potential difference of 10 to 100 microvolts. Now, our bodies are electrical systems. You can do the same thing for the heart. Cells in our human body, well, cells in any living creature can have potential differences across membranes. Cells in a human body, we've got about 100 millivolts for that source of that potential difference. A battery, the little batteries we put in everything around our houses, 1 to 10 volts. Household electricity is 100 volts. Static electricity can generate a lot of potential. The electricity that's traveling long distances in power lines, 500 kilovolts. And we'll use some of these later in different problems. We're going to apply this idea of work and the change in potential and the definitions we just went through in order to think about how electrons travel in a headlight, let's say, of your car. This is a great example. Here we have a 12-volt car battery. When a 12-volt battery runs a 30-watt headlight, how many electrons pass through the headlight each second? In order to solve this problem, we need to know a little bit more about how electrons move within a system. So electrons always flow, let's say, they flow from negative to positive ends of a terminal. Okay, so Ben Franklin, when he was first thinking about electricity, he thought that electric charges flowed from the positive to the negative terminal of a battery. But actually, it's the electrons that are doing the flowing and they flow, they move from the negative end of a battery to the positive end of a battery. So we're going to have electrons that are going to be moving from the negative terminal, which I'm calling terminal A, so that's our starting point, all the way through the headlight and then back to terminal B, which is our end point. Here we have my sketch of the battery. We've got a 12-volt potential difference between point B and point A. So with this problem, we have a 12-volt battery. That means that our quantity delta V, our change in potential, equals the potential at point B minus the potential at point A, and that's 12 volts. And so this property is how we often define batteries. And this is what it means. That's the potential difference between the terminal of the battery, and that's going to encourage electrons to flow within the circuit that will be formed. And then with this problem, we're also told that our battery runs a 30-watt headlight. So the power delivered to the headlight is 30 watts. How did I know that was a power? Well, it didn't tell me specifically in the problem that this was a power, but if I see the unit of watts, I know that that must be a power. So 1 watt is a joule per second. And our problem asks us how many electrons, so we'll say N electrons, pass through our headlight each second? Question mark. Our battery in this case is losing energy to move the electrons from the negative terminal to the positive terminal. So in this system, we've got a change in electric potential energy, and that change in electric potential energy is equal to negative 30 joules each second, okay? Again, our battery does work, so it's losing energy. So the change in potential energy in this system here is going to be a negative quantity because our battery is losing energy in this process. We need to figure out the number of electrons that flow through our headlight each second. To do that, we can use this equation that we just saw, that the change in potential energy is equal to the charge times the change in potential, or the potential difference. And since our problem is asking us for the number of electrons each second, we can evaluate this equation at each second, for each second. So for each second, we know that our battery loses 30 joules of energy. And we know that we have this potential difference of 12 volts. Then in each second, the amount of charge we can move through the headlight will be minus 30 joules divided by 12 volts. And that gives us a number of minus 2.5 coulombs. So in each second, we're moving minus 2.5 coulombs worth of charge through that headlight. How did I get coulomb? Well, we've got a unit of joule on the top here, and then we're dividing it by a volt, which was a joule per coulomb. So we're left with essentially an inverse coulomb, 1 over 1 coulomb, and that gives us back a unit of coulomb. To find out how many electrons that is, we just multiply that by the fact that, we'll use a little conversion factor, that 1 electron has minus 1.6 times 10 to the minus 19 coulombs worth of charge. And that tells us then, if we take 2.5 divided by 1.6 times 10 to the minus 19 coulombs, we get 1.56 times 10 to the 19 electrons that pass through this headlight each second. So that's how we can solve this particular problem. We had to use a lot of ideas: power, change in potential energy, and we had to incorporate some of the definitions that we just learned in the previous slide in order to answer this question. The energy associated with a single electron is incredibly small. Yeah. So we have to define a new unit of energy on the sub-microscopic scale. 1 electron volt is the energy given to a fundamental charge, so let's say an electron, accelerated through a potential difference of 1 volt. So that's the definition of an electron volt. 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. We know that the charge on 1 electron is minus 1.6 times 10 to the minus 19 coulomb. So the energy associated to move 1 electron through 1 volt is 1.6 times 10 to the minus 19 joules. Here we have 2 parallel plates. One plate has a negative charge, the other plate has a positive charge. And so the electric field between these plates is pointing from our positive charge away from the positive and toward the negative. So the electric field between these plates is running from the positive plate to the negative plate. We place our electron inside this electric field. This electron is going to want to move to the right inside this field, and we have a kinetic energy associated with moving this electron through 1 volt of a potential difference. And this image is actually an example of something called an electron gun, and it accelerates electrons using a potential difference between 2 metal plates. Anytime you have a potential difference, you also have an electric field there, and you can use that potential difference in order to move charges. So we're going to use this idea of potential differences and work and conservation of energy in order to understand how charges move within a potential difference. Mechanical energy is the sum of all the kinetic energy in a system plus all of the potential energy in the system. And in this case, since we're thinking about these small charges, we're going to think about not the gravitational potential energy, but the electric potential energy. Our conservation of energy equations still hold. We've got the initial kinetic energy plus the initial electric potential energy equals the final kinetic energy plus the final electric potential energy. We could combine conservation of energy with this idea that you can accelerate particles if you have a potential difference between 2 points, again, in order to see how particles move within this potential difference. Here's your engagement check for this mini lecture. And this is a graph of the electric potential in a system. The vertical here is the electric potential, and X is our position away from, let's say, X equals 0 on a number line, okay? So the potential at some point X in the system is given by this red curve here. We can place our charges anywhere along this x-axis, and just by looking at this potential curve, we can know in which direction our particles are going to move. So when released from rest, positive charges accelerate from regions of high potential to regions of low potential. And when released from rest, negative charges accelerate from regions of low potential to high potential. So when we've got our battery connected by wires within a circuit, our electron, which is the charge that carries which is the charge that flows when we think about electricity, our electron is going to travel from the low potential, which is the negative terminal of the battery, to the high potential, which is the positive terminal of the battery. Now, these are the 2 questions you're going to answer based on this graph here. Let's say we have a positive charge. If a positively charged particle is placed right here at point A, what will be its subsequent motion? So using what we just described down here, I'm going to place my positively charged particle at point A. At point A, this is the electric potential. Okay, The electric potential gets larger and more positive as we move to the right. The electric potential gets smaller as we move to the left, and it eventually becomes negative down here. Okay, so we're placing our particle right here. It's subject to this electric potential, the shape of this electric potential curve. What will its motion be? Will it go to the left, go to the right, stay in the same place, or oscillate around some point? Now we're going to place a negatively charged particle at point B, and we're going to give it a small kick to the right. Okay, give it a small kick to the right. What will its subsequent motion be? Right here, if we go to the right, the potential decreases. If we go to the left, the potential also decreases. In order to answer this, you will again refer to these rules down here that explain how a particle of a particular charge accelerates within an electric potential.